calculate the whole thing, the difference between the two, is it divided by kappa, it's times kappa? Nope. Yeah, it's divided by kappa. There's going to be less charge in this region than on the other side, by about a third. So it's going to be, give or take, 1.6 or 1.7 times 10 to the negative 7. Don't exactly know what the answer is, 1.6, 1.7. I'm going to say 1.7. Correct me on that, but it's about 1.6 something. That's 4.5 divided by 2.94. Oh, so it's actually small. I was thinking it was going to be, that 294 was going to be different. So it's still going to be about 1.5. So my rounding has its limitations. Is that kind of capiche? So what's the effective capacitance from one side of this region, from one conductor to the other? What is the effective capacitance of this arrangement? I'm going to call it the net capacitance. Sometimes we use effective or equivalent capacitance. I'm just going to say that for now. Let's do this particular nomenclature later. Well, to approach it analytically, I'm going to take this tack. Whatever the capacitance is, it's going to be equal to the total charge stored divided by this voltage, period. Two conductors, they're separated, there's some interaction between the plates because of their induced charge. This is the case. The Q total corresponds to Q1 plus Q2. And we'll note that Q1 over delta V divided plus Q2 divided by delta V is essentially the capacitance in C1 in the C1 region plus the capacitance in the C2 region. You'll get the calculation equation in your engineering class. I'm going to show you where it comes from, why this works the way it is. So we never actually calculated the net charge. But basically, if we took 6 times 10 to the negative 7 and divided that by 25. That's going to give us a value of
2.4.
joules per coulombs per volt, excuse me. More fair. So previously it was 3.6, but when we fill it halfway with air, remove half the dielectric, if you will. It drops because there's half the dielectric. but it's larger than what it would be in air. We didn't actually calculate it for air, did we? But ultimately, the combined current voltage response is a combination of capacitive contribution of both regions independently.
Well, we know for air it's going to be pretty close to 1, because it's 3.6 divided by 2.94.
I think 1.2 or so.
Right.
So it's somewhere between 3.6 and
Which makes sense.
It's halfway in
1.2.
between the two.
2.4 is halfway between 3.6 and 1.2.
We could calculate the capacitance in each region if we wanted to. Yeah, just did all that. Okay, so now before we take our break, I'm going to add one little caveat to, or thought scenario to this. How would this net C differ if the two distinct regions were physically split apart and separated? Now, the situation I'm thinking about is I'm going to keep the same voltage. So I want to keep their connection.
Yeah, I don't see how it would differ.
If this is plus and this is minus, this is plus and this is minus. Does that change? If that doesn't change, does the electric field in between the two conductors change on either side? They don't change. So the amount of charge that's stored in the dielectric region does not change when these two are split apart compared to when they're just sitting next to each other. Nor does the air-filled region. We call this type of a connection a parallel connection because we take two things and we connect their ends together. So we call it a parallel arrangement. In this case, on capacitors. For some of you, that was obvious. You knew maybe that was coming. You read the book, or just you've known it from previous classes or otherwise. But ultimately, what we can say then, and I'm just going to say this in words, I'm going to write this down. When you have two capacitive regions that are separated but still somehow connected by the same endpoints, they're in parallel. There's no difference between having them physically separated and having them right next to each other. But the net response, or the net result, is that the total effective capacitance is the sum of each of the parts individually. Which from electric circuits is exactly ass backwards from the way resistors work. If you want to think about that. So it's important to sort of distinguish. So for this type of an arrangement, whenever you have capacitors in parallel, it's always the combination of the individual capacitors additively. So let's take a break on that. And let's come back and look at the other obvious situation.
It's weird. It's actually the opposite.
Okay, see, I haven't, since I've gotten my disposable pens, I haven't had to worry about it for too long, but, see, I've got a noodle arm now because I don't throw 5 pens a day in class. So I got my new supercharged
So what do you just take those home?
ink pen 10,000s right
You
here.
fill them full of juice when you get home or something?
No, they actually buy me the juice for them, but there's these little ink cartridges in the bottom. Yeah, you just slam those babies in there, it's just like a little nice comfortable bolt-action rifle. There you go, rock talk, ready to rock, right? Okay, so let's look at the second part of this. And by the way, lest I forget, read chapter 26, at least just review it moving forward. Most of you have had some electric circuits, but I think our circuit lab this week is the building of a voltmeter and an ammeter, is that right? It's engineers, good example, half of what engineers do, and the old mantra used to be, you want to win a Nobel Prize? Figure out a way to measure something better. That simple. Now it's not so much the case because we're kind of tapped out with our ways to measure a lot of stuff. But after NMR, magnetic resonance, there aren't that many ways left that we've discovered in a while. But that was a big thing. There are ways. There are more things to do, but that's sort of the big thing. If you can figure out ways to measure things that are cheaper, faster, more efficient, more accurate, you know, win yourself a Nobel Prize.
Yeah.
So that, you know, it's Einstein won his Nobel Prize for the photoelectric effect, not for relativity. So that's rules to live by. Now, what happens on the flip side of our problem? If you were to take same dimension of a capacitor, but fill it with a dielectric this way instead. Same D, same V, everything else the same. So basically sandwich, and here's a dielectric, if you will, sandwich 2 dielectrics between the plates rather than squishing them sideways. What happens to the electric field?
It's the same. Field better be the same.
Tough one to think about, isn't it? So you put you build up charge, and as you build up charge, your electric field has to be the same through this thing.
Right.
So, well, think about it this way. How did the net electric field change when you had an air-filled capacitor this way and this way? Is the voltage to distance ratio different here than it is here? So specifically, there's not necessarily a reason why it has to be. Okay, so you got to be, think about this in sort of a interesting way. So you've got an electric field here, you've got an electric field there. They ought to be the same.
Okay.
Now, think about what has to happen. If you have an electric field here, this edge, you got the field going down this way, what's the direction of the induced polarization in here?
The other.
Backwards, right? So you're gonna get a plus here and a minus there, which will functionally affect the V over D here. So it's a very strange combination that has to happen here. To look at it though, I want to separate it and take a step back and look at it the way we looked at the parallel capacitor after we broke it apart. I'm going to start there because it's probably easier to approach it. The problem with doing it this way, as I look at it and as I think about it, is that because the dimensions now of D are going to be different, it's a little bit more tenuous. So I want to simplify the argument a little bit. So let's look at it as two successive capacitors in series, if you will. Successive, yes. And what do we have? So we've got air, and we've got the dielectric. And each of these is a D over 2 size thing. So we're going to always have the problem of this D not using the same one as the previous one. And there's your plus, there's your minus. So we've got 25 volts between the two ends. Now, lest this look odd, think about it this way. At this interface, regardless of what the electric fields are doing, at this interface between the voltage, the potential difference is going to be the same. The voltage value is going to be the same. So the question then becomes, how much charge is stored in this thing? How much charge gets stored? Let's call this Q1. Let's call this Q2. How much charge gets stored on each face of the capacitor?
Would it be 2 cubes and just add them together? Because you get more charge on the dielectric.
I won't
capacitor,
say
but it
yes
would
and I
shove
won't
more.
say yes and I won't say no, but I'll say, can you justify why it would be doubled?
Well, because, so you have the whole setup and you'd have a larger charge on the bottom capacitor with the dielectric, and then in between, that's going to induce the charge of the same magnitude to the bottom plate of the air one. And since they have to be the same magnitude on the capacitor, that means the top one would also be the same.
Reasonable logic, but let me ask the question, what do we know about separation of charge on a conductor? If it's neutral, what do we know about the charge separation?
It's neutral.
Got to have the same number of pluses as minuses?
Right.
So, if this capacitor is charged, you're going to have a plus here, I guess I should have put a minus there, a plus here and a minus there. Where do these electrons come from? There's no battery. Where do they come from?
They get pushed away from
they get pushed away from this here. This is another polarization example, if you will. So whatever charge ends up here comes at the expense at this end. But however much charge you have here is going to limit the amount of charge you have on this end, because you're going to have the same balance. Same here. However much charge gets pushed up here is going to be balanced by how much charge is here. So when they're aligned this way, you cannot have more charge on the top than you have on the bottom. So Q, put that minus over here somewhere else, or change colors or something. This Q is this Q. So let's just call it a total Q, plus there and minus there.
That would mean that the electric field can change.
What charges is here? Total charge.
Don't you look at the pun.
That's from the video. What's that? That's from the video.
So
So basically he's going over that part.
what are the consequences of that?
Sick. I love these videos.
Exactly. So we might start by saying, well, C1, C2. C1 is going to be related to epsilon naught, A d over 2, it's separation distance, use the same. And C2, the only difference is the epsilon. And I just put the 2 on top, the d over 2 on the bottom. And the total charge, Q, should be equal to C1 V1 and it should also be equal to C2 V2. That'll be the same value. So, how might we approach this farther? Help me out here, guys. Work with me.
I guess we need to find the voltages.
Put some more information in here. We're gonna certainly have a V1, V2. Catch myself doing these things. How about this? We might say that across the entire piece, the ratio of Q to the total delta V should be representative of some net capacitance. And since delta V is the combination of the voltage across the first and the second, it's potential energy. So you're going from one side to the other, you're climbing down a hill if you go 25 volts. Combination of the two is your total voltage. So Q over delta V would correspond to Q over delta V1 plus delta V2. Which is, if you will, another way of saying, let me change colors here. If I solve for delta V1, it's Q over C1. So I have over here Q divided by Q over C1. Plus, if I play the same game for the voltage across the second one, the voltage across the second capacitor is going to be the same Q. We divide it by whatever that second capacitance is. And what we might notice is that on one side we have Q over delta V, and on the other side we have the cancellation of Q's, or if you will, 1 over the inverse of C1 plus the inverse of C2. This would be the equivalent of the total or the net capacitance from either side, top to bottom. You've probably seen it written this way. Take the inverse of both of those just to make the number a little bit easier to write. I'm not sure why we even do that anymore, because with our scientific calculators, it's so easy just to calculate inverse quantities anyway. But if we divide both sides into one, then what we're left with is the inverse of the net capacitance, which, by the way, is voltage divided by the total charge, equal to the combination of the first capacitor, inverse, when added to the inverse of the second capacitor. And if we just want to put pieces of the puzzle in here, what would we have? So we would have D over 2 epsilon naught A plus D over 2 epsilon A.